Thank you, Mr. Pensa, for this introduction, and thank you to give us this possibility to talk to you about our work. So my name is Laurent Spinelle. I'm coming from the GRC, Joint Research Center in Ispra in Italy, but this time in the north of Italy, not south. I will talk about calibration of cluster of low-cost sensor. So we took a huge amount of sensor, low-cost sensor, and we tried to calibrate them using different methods, only for the measurement of air pollution in ambient air. This work was done in the ambient of the MACPOL project, Euromet project, that ended in May of this year. In the first part of the project, we tried to validate and calibrate sensor using a full, I will try to have a laser, a full design of experiment passing through at least 100 steps and experiment, leading to a validation of our laboratory experiment on the field. Here, we try to do all on field, only on field. First, this is our facility, our measurement facility. We used a mobile laboratory placed in a semi-rural site. We were able to measure 5 compounds: ozone, NOx, SO2, CO, and we placed more or less the same sensor, the same gaseous sensor at the top of the mobile laboratory to have measurements that can be compared easily. The first type of validation calibration we used was the simple one, the linear regression, that maybe you know, but I just write some simple ID. Linear regression depends on sensor. Their sensor measurement depend obviously on the exposure conditions, that is humidity, temperature, all interfering gaseous compounds that may react with the sensor. The second one was multilinear regression. So in this one, we can integrate more data, and but we need those data. So we need our analyzer to have reference measurement or other gaseous sensor. Let's focus a little bit on the ozone one, that was the most efficient. If we talk about the O3A1F, that gives the best result. Using only linear regression, we achieve correlation coefficient of 0.87. That was not bad at all. It was working very well, but we reached to improve those values using only NO2 measurement coming from an reference measurement analyzer to 87 to 91. That was very, very interesting. But for the other sensors, that was not so easy to reach a good value of correlation. This is more or less what we obtained looking at the data after the calibration. So we took the formula we obtained during our analysis, and we applied them for the full length of our experiment measurement. And as you can see, for the left part, we have the linear regression value, which are the predicted sensors on the y-axis and the ozone measurement coming from the analyzer on the x-axis. You can see that's not bad. There is a little bit of the results are wider in the low concentration, but we can see a type of linear response. We achieve a correlation coefficient of 81 that was near from the one I showed before. For the multilinear regression, using the NO2 value coming from the analyzer, we increase a little bit those correlation factor, but not 91, only 0.82. That was not so good, and we keep more or less the same shape of data. The last calibration method we used was the artificial neural network based on the multilinear perceptron method. So we put a lot of data into our neural network. Using some selectivity technique, we found that only 3 sensors was useful. the one of ozone, one of NO2, and one of CO. I think there was more or less 2 or 3 hidden nodes inside the neural network that can change the weight of each data, and we reach to find a good compromise in the value. Those are the scatter plot of the predicted value against the reference measurement. As you can see on the left part, already on raw sensors, so without any data treatment, they are what they are, and we just apply the neural network. We achieve those 0.91 for the correlation factor. That's very good. And when we try to implement already calibrated or corrected measurement using temperature, humidity, or any gaseous compounds that the sensor were sensible to, we decreased a little bit those correlation from 91 to 86. So this is more or less a way to summarize a little bit what happened for ozone. We plot the uncertainty calculated with the formula you have on the bottom left for each model, and we plot them as a function of the concentration of ozone. As you can see, for the pink and green line, we did not achieve a low uncertainty level, only 60% more or less of uncertainty, and the value tends to increase for high concentration. This is mainly due to a drift in the sensor value for those LM linear model and multilinear model. Talking about the last one, which were artificial neural network, we tried 3 different data sets. The raw one in black, the blue one for standardized data, and the red one for the pre-calibrated data. Blue and black, so raw and standardized, are more or less similar. They are just different at high concentration, more than 60 ppb of ozone. The red one gives the best results, but it's clearly different and clearly higher in the low concentration. So I plot also on those graph the DQO, which is the data quality objective set up by the European Commission at 30% of uncertainty for ozone, and the limit value at 60%. At this level, so 60% and 60 ppb and 30%, we can see that only a neural network can be used to meet the data quality objective. We did the same for all the other gaseous species. For NO2, the results were very different. I will not talk about LM air and ML so linear and multilinear, because they were really out of range. Just artificial neural network. The best was, again, artificial neural network based on pre-calibrated data, but they need a lot of other input. They need reference measurement to correct the sensors data, the basic sensor data. The other one, neural network and artificial neural network on standardized data, were promising for low concentration, but in our station, we did not reach a very high level of concentration, only 40 ppb at maximum. And we can see that at those level, the uncertainty tend to increase. This is maybe due to other sensor effect, I don't know, but for sure, it's not, let's say that the data quality objective is not met for NO2. We also decide to plot those information using a target diagram. A target diagram shows if our model more or less can fit into an uncertainty range, here showed as a target cycle around 1 for on the graph. I plotted on the x-axis the centered standard deviation, which is the root mean square divided by which is the unbiased root mean square, sorry, and on the y-axis, the bias. As you can see here, as you can try to see maybe, the only dots which are inside the circle, so the target circle, are the red one. The red one corresponds to the ozone one, the most efficient one on our side. For the black one, which correspond to the NO2 sensor, the only one that is nearer from the circle are the one corresponding to the artificial neural network. All LR and MLR were showing a very high root mean square of error. That's saying that let's say that I will say it at the end. We also did it for NO. For NO, it was very bad. Also, the artificial neural network based on pre-calibrated data was not. We cannot reach a real good uncertainty. The lowest one was more or less 70% for the neural network on uncalibrated data, so on raw data. For CO, more or less the same. On our side, there is only a small concentration of CO. We reach anyhow low uncertainty using the neural network on pre-calibrated sensor value. And finally, for CO2, this was really easier because the level is higher. We reach a real low uncertainty with the neural network, both standardized and raw data, more or less 5% of uncertainty at 440 ppm. This is the last slide. So more or less, we can conclude that those famous data quality objectives can be met for ozone sensor, even if it needs a lot of computing, post-computing. It can maybe be met for NO2, but we will need more experiment and more NO2 in our case, so maybe another site. We only reach high uncertainty for NO and CO. It's likely that the data quality objective cannot be reached at this moment. And for CO2, we observe a very low uncertainty down to about 5%. We have seen that the easiest model, linear and multilinear, were given the highest uncertainty. For the artificial neural network, the best correlation, and obviously the lowest root mean square was given by the INN standard and RAW, most of them. When we use reference data, we have seen sometimes a decrease of the measurement uncertainty, sometimes yes, mainly a decrease of those uncertainty. And finally, we have seen that even if we are not using reference data, such as temperature, humidity, or other gaseous species, we can solve, let's say, the current sensitivity of each sensor only using post-computation, post-treatment of the data. Thank you, all of my colleagues. Thank you again, Mr. Pensa, for this opportunity. And if you need more information, you can download our report on this server, or you can directly send us an email, and we will be happy to answer your question.